impedance, phasors, and transition from DC to everything else. Here's a simple DC circuit. Has 3 resistors, 1 DC source, 1 switch that closes at t equals 0. Current is the battery voltage divided by the sum of the resistors. The voltage across R2 is the current multiplied by R2. And all this happens as soon as the switch closes. Ho hum, no big deal. DC analysis is easy. Well, it's easy now because we're familiar with it. This circuit is similar. It has a resistor, capacitor, and inductor, 1 voltage source, 1 switch that closes at t equals 0. What can the voltage source be? What can the voltage source be? Could be a sinusoid with phase and voltage shifts, step function, ramp, exponential, delta function. Holy moly, how can we deal with all these possibilities? It's easy with Laplace and phasor transforms. We simply transform all components into the S domain or J omega domain, and then apply all the DC rules using complex numbers. And finally, the inverse Laplace or inverse phasor transform to return to the time domain. What is a phasor and phasor transform? This complex number in polar form is a phasor if it represents the sinusoid with amplitude Vm and phase shift P. In other courses, Vm over the square root of 2 may be used instead of Vm in the definition of the phasor. We use Vm in this course because it's easier for our purposes. So when do we use phasors? Phasors are used in AC steady-state circuits. No switching is allowed. So what is a phasor? A phasor is a complex number that represents a sinusoid. It has amplitude and phase shift. The sinusoid frequency is important and known, but it's not in the phasor. Now, what about the resistor, capacitor, and inductor? Well, we have complex numbers called impedance that represent the resistor, capacitor, and inductor. What is the impedance of a resistor, capacitor, and inductor? First, we'll define impedance in a general way that will allow us to deal with all these voltage sources. S-domain impedance is defined as voltage over current as a symbol of Z and units of ohms. The S-domain impedance of a resistor is R. This is the rigorous formal definition. S-domain impedance of an inductor is S times L. S-domain impedance of a capacitor is 1 over quantity S times C. These rigorous definitions of S-domain impedance for resistor, inductor, and capacitor permits us to easily analyze circuits driven by all these voltage sources and more. Please review these derivations of impedance until you thoroughly understand them. They're all based on the Laplace transform property that derivative in the time domain is equivalent to multiplying by S in the S domain. Now, what about J omega domain impedance? Here's the S domain impedances of all 3. Just setting S equal to J omega will transform from the S domain to the J omega domain. And here are the J omega domain impedances of the 3. J omega domain is the same as phasor domain. Phasor impedance is a complex number and allows us to analyze AC steady-state circuits containing resistors, capacitors, and inductors. In summary, given a circuit without a switch and containing resistors, capacitors, and inductors, and the voltage source is a sinusoid, transform all components into the phasor domain, use DC circuit laws to solve for everything else, finally transform back to the time domain. All voltages and all currents will be sinusoids with the same frequency as the source.